Hello everyone, this is Professor Ng Chi Kun from Unimas. In this video, I'm going to give you the tutorial solutions of question 7 in tutorial 2. So in question 7, we have a figure 2 here of a continuous beam, span AB and BC, with span AB of 7 meter and span BC of 6.5 meters. So this continuous beam has approximately equal span, having cross-section of 250 mm by 500 mm. The beam supports its self-weight plus a superimposed characteristic unfactored uniform permanent action of 16 kN per meter and a uniform characteristic variable action of 10 kN per meter. So in this example here, we use concrete grade of 30, steel grade of 500, and specific weight of reinforced concrete is 25 kN per cubic meter. Concrete cover is 35 mm. Exposure class is XC3, and the largest aggregate size is 20 mm. We assume supports A and C are pinned. So from A to E, we have to analyze the beam using the approximate method outlined in BS 8110 Part 1, 1997. B. Design the longitudinal and shear reinforcements for span AB. Assume that the beam section as rectangular. After that, check for deflection and crack control. C. We design the main reinforcement for support B. D. We design the longitudinal and shear reinforcements for span BC by assuming the beam having rectangular section. After that, we check for deflection and crack control, and then finally we sketch the reinforcement details. So the first step in design is the analysis. So in this example, we have beam cross section of 250 mm by 500 mm. So the self-weight of the beam in terms of load per unit length is width multiplied by height of beam multiplied by the unit weight of concrete. So we get 3.125 kN per meter. So that gives us the design action of 1.35 times 3.125 plus 16 in bracket plus 1.5 times the characteristic variable action of 10 kN per meter length. So we get total design load as 40.8 kN per meter length. After that, we calculate the total load on span AB. So the total load on span AB is the uniformly distributed load multiplied by the span AB of 7 meters, so we get 285.6 kilonewton. And then we calculate the total load on span BC, where we use uniformly distributed load of 40.8 kilonewton per meter multiplied by the span of BC, which is 6.5 meters, to get 265.2 kilonewton. So the loading on the beam is 40.8 kilonewton per meter length, and then the length of AB is 7 meter and the length of BC is 6.5 meters. So next we want to get the shear force and bending moment diagrams. So for this we use the approximate method given in BS 110 Part 1 1997. So this method can be used when the spans of the continuous beam are approximately the same. Approximately the same meaning that they are within 15% difference, 15% difference. And the loading is also within 15% difference in the beam. So this is the table that we use to determine the bending moment and shear force on a continuous beam with approximately equal span and approximately similar arrangement of loads. So first we look at shear force. So the shear force at the outer support is 0.45 times F, where F is the total force on the end span. And then near the middle of the end span, there is no shear force, it's almost zero. And then at first interior support is 0.6 times the total force on the span of the end span. And then at the middle of interior spans, there is no shear force. The shear force at the middle of the span is almost zero. And then at the interior supports, the shear force is 0.55 times the total force on the span. As for bending moment, we assume zero moment at the outer support. So at the end support, the moment is zero. And then near the middle of the end span, we have a positive moment of 0.09 F times L, where F is the total force on the span and L is the span of the beam. And then at the first interior support, we have a negative moment of 0.11 FL. And then near the middle of interior spans, we have positive moment of 0.07 FL. And then at the interior supports, we have negative moment of 0.08 times FL. So for the shear force diagram, this is the outer support shear force. So we have the shear force is equals to 0.45 F. So this is span AB, so we use FAB. So we get 142.8 kilonewton as the shear force at A, at the support A. And then at support B, we have two shear forces. One is on the left hand side here, and then the other one is on the right hand side of support B. So on the left hand side of support B, we have BBA. So this shear force is 0.6 times F and is negative because it's a negative shear force from this shear force diagram. So we get negative 171.4 kilonewton. On the right hand side of support B, we have BVC. So this is based on span BC because it's on the right hand side of support B. So we have span BC. So 0.6 times the total force on span BC is 159.1 kilonewton. And then at support C here, we have VC. So this is the outer support. Okay, so at outer support we have 0.45 F. So this is for span BC, so it's FVC. And we put a negative sign there because it's a negative shear force. So we get negative 119.3 kilonewton. For the bending moment diagram, so at the outer support we have zero moment. Okay, and at this outer support here we also have zero moment. And then near the middle of the end span here, we have 0.09 FL. So this is span AB, so it's FAB, and the span is LAB. And we get 180 kilonewton meter as the moment near the middle of span AB. And then at support B here, so based on span AB, we have one moment, and then based on span BC, we have another moment MB. Okay, so from here we get two moments, but we choose the one that is having the largest magnitude as the design moment. So the one having larger magnitude will be the one with the longer span, which is span AB of 7 meters. So MB, supposedly we have another value which is 0.11 FBC times L BC, but this one is a smaller moment as compared to the moment that we have calculated here. So we just use this moment of 0.11 FAB times LAV, which is equals to negative 220 kilonewton meter. It's a negative because it's hogging moment. And then this is the moment near the middle of span BC. So span BC is also considered as an span. So for n span, near the middle of n span, we have 0.09 FL. So this is span BC, so it's FBC and LBC. MBC near the middle of the span BC is 155.1 kilonewton meter. Now we want to start designing. So first of all, we look at span AB. So span AB, the design moment is 180 kilonewton meter. So the ultimate bending moment MED is 180 kilonewton meter. And the ultimate shear force VED is 171.4 kilonewton based on this value, which is on the left hand side of support B. The shear force at support A is smaller, so we use a larger shear force magnitude in our design. So in design, we don't have to put the negative and positive sign. We just design for the magnitude of the values. So for the effective depth, we have H minus the cover minus the diameter of the link minus half diameter of the main bar. So in this case, we assume there is only one layer of main bars, so it's minus main bar diameter over 2. So we get effective depth of 449 mm. So K balance is 0.167 because there is no redistribution of moment. So we calculate K, which is m over FCK BD square, and it gives 0.119, and this is less than K balance, so no compression reinforcement is required. So after that, we calculate the moment arm Z, which is 0.88 D, and then we calculate AS, which gives as required of 1047 square millimeter. And then based on section 9.2.1.1, as minimum is given by this expression and it should not be less than 0.0013 BD. So from table 3.1 for grade 30 concrete, FCTM is 2.9 megapascal. So as minimum as calculated is 169 millimeter square, and this is larger than 0.0013 BD, so it's okay. So as minimum is 169 square millimeter. And then as max is 4% of the concrete cross section, so 4% of concrete cross section is 5000 square millimeter. So as max is 5000 square millimeter. So we use 4H20 to give as provided of 1257 square millimeter. Next, we design the shear reinforcement based on section 6.2.3 of Eurocode 2. So the design shear force is 171.4 kilonewton. So based on this design shear force, we first calculate VRD max at 22 degree and at 45 degree, and it was found that the design shear force BED is smaller than VRD max at concrete strut angle of 22 degree, so we use the theta value of 22 degree in our subsequent calculation. So for shear links with two legs, the ASW over S is calculated based on this expression here, which is simplified into this expression here to give 0.392 value. So we try link with 6 mm diameter, so that gives the cross-sectional area of steel of 56.6 square millimeter for two vertical bars for two legs. So the spacing calculated is 144 mm. Based on section 9.2.2 in bracket 6, maximum spacing is 0.75 times the effective depth D, so it's 337 mm. And then based on section 9.2.2 in bracket 5, minimum links is given by this expression here, and we get 0.392 219. So this one we get spacing of 258 mm. So based on these three spacing here, we use links of H6 at spacing of 125. We know that the H6 at spacing of 125 shear links are only needed near the supports where the shear forces are higher. For the lower shear force portion of the beam, the minimum shear links of H6 at spacing of 250 is sufficient. So this 250 is based on minimum links that gives maximum spacing of 258 mm. So the angle theta is less than 22 degree, but we conservatively take it as 22 degree in our calculation. Therefore, the shear resistance of minimum links is given by this expression here, which gives V mean is 99.1 kilonewton. So meaning that when the shear force is 99.1 kilonewton or less, we can use H6 at spacing of 250. So from the shear force diagram of span AB, we know that this distance is 3.2 meter and this distance to zero shear force is 3.8 meter from support B. So based on these two values and from proportional triangle with the value of maximum shear force of 142.8 kilonewton and V mean of 99.1 kilonewton, we can determine this distance here, which is approximately 1 meter. And then on this side of the triangle here, okay, with proportional triangle, we also can determine this distance, which is approximately 1.6 meters. So here we can use the shear links designed for higher shear force and also for this side. And then for this region of the beam where the shear force is less than 99.1 kilonewton, we can use the minimum link of H6 at spacing of 250 mm. And then for the additional tensile force at support A, we use the shear force at support A to calculate delta FTD, that gives 178.5 kilonewton. So we calculate the additional tension reinforcement based on delta FTD of 178.5 kilonewton, and we get the area required is 410 square millimeter. So based on the simplified rule of Curteman, the required tension steel for bending at support A is only 25% of as required at midspan. So that gives 0.25 times the as required near the midspan is 1047 square millimeter, and that will give us 262 square millimeter. So the total as required near support A is 262 plus the as from delta FTD, so that is 672 square millimeter. So to provide the steel, we still have to use 4H20, because if we curtail the bars to 2H20, then it will be less than 672 square millimeter, where it only has 628 square millimeter. So therefore, we cannot cut away any of the 4 bars towards support A. Next, we calculate the deflection for span AB. So we calculate rho, which is equals to as required of BD, to give 0.0093, and then rho 0 is 0.0055, and then there is no compression steel required, so rho prime is 0. And then from table 7.4n, for the end span of continuous beam, we use K of 1.3. And then rho is greater than rho naught, so we use equation 7.16.b. So we calculate the L over D basic to give 20.6. And then modification factor for span greater than 7 meter is still 1 because the span is 7 meter. It's not more than 7 meter. And then the modification factor for steel area provided is as provided over as required. So we get 1.2 and is less than 1.5 is okay. Therefore, the allowable span to depth ratio is 20.6 times 1 times 1.2, so we get 24.7. The actual span to depth ratio is 7 meter over 449 mm, so it's equals to 15.6, and this is less than the allowable L/D ratio, which is 24.7. So checking for deflection is okay. For crack control from table 7.1n, we have limiting crack width is 0.3 mm for exposure class XC3. After that, we calculate the steel stress by assuming that we have a quasi-permanent load at serviceability limit state. So we have GK plus 0.3 QK as our quasi-permanent load. So GK is 19.125 kilonewton per meter and QK is 10 kilonewton per meter. And then S required is 1047 square millimeter and S provided is 1257 square millimeter, and the steel stress Fs is 196 Newton per square millimeter. So from table 7.3n, with steel stress of 200 Newton per square millimeter or less, the maximum bar spacing is 250 mm. So for the bar spacing, we have 4 bars at the bottom of the beam. So the spacing is calculated using 250 mm minus 2 times the cover minus 2 times the shear link minus 2 times half diameter of the main bar, and we get spacing of 49 mm, which is less than 250 mm, so it's okay. We also need to calculate minimum distance between bars based on section 8.2 of Eurocode 2. So from the spacing of the bars, we can calculate the clear spacing, which is the spacing minus of 2 times of half bar diameter, so that is 29 mm. So the clear spacing must be larger than the maximum bar size, so this is okay. And then the clear spacing must be larger than the aggregate size plus 5 mm. So largest aggregate size plus 5 mm is 25 mm. So 29 mm is larger than 25 mm, so it's okay. And then the clear spacing must be larger than 20 mm, so this one is also satisfied. So all 3 requirements are satisfied for the minimum distance between bars. Now we move on to the design for support B. So at support B, we have design moment of 220 kilonewton meter. So we do not need to put the negative sign in design calculation. And then the maximum shear force at support B on the left hand side of support B is 171.4 kilonewton, which is the largest shear force at support B. And then we assume 2 layers of steel at support B. So because support B is having negative moment or hogging moment, so the tension reinforcements are on the top of the beam. So in this case, we assume that we have 2 layers of bar, so the effective depth is calculated in this manner, where it is the height of the beam 500 minus cover minus link diameter minus 1 diameter of the main bar to give 439 mm. So there is no redistribution that gives K balance of 0.167. And then we calculate K value, we get 0.152 is less than 0.167, so no compression reinforcement is required. And then the moment arm Z is 0.84D as calculated, and that will give as required of 1371 square millimeter. And then as minimum is calculated using this expression, and it should not be less than 0.0013 BD. So we get as mean as 166 square millimeter, and 0.0013 BD is 143 square mm. So the as minimum is 166 square millimeter. And then maximum reinforcement is 0.04 BH, so we get 5000 square millimeter. So we provide steel of 6H20 to give as provided of 1885 square millimeter. So we arrange the reinforcement with 4 bars as the first layer, and then 2 bars at the second layer. So based on this arrangement, we calculate the effective depth for this group of bars by using the principle of moment of area. So D1 is the effective depth for the first layer of 4 bars. So D1 is 449 mm, and then D2 is the effective depth for the second layer of the 2 bars here. So D2 is 429 mm. So the total steel area of 6 bars multiplied by the effective depth is equals to the area of 4 bars multiplied by its effective depth plus the area of the 2 bars multiplied by effective depth of D2. So this must be equal. So we have D equals to 442 mm, which is larger than the D that we assume in the calculation. So in this case it's okay. So now we know that the actual effective depth is 442 mm. If the calculated effective depth here is less than the assumed value, then we have to use the smaller d value to repeat the calculation. And then we calculate the additional tensile force at support P, where we have the design shear force of 171.4 kilonewton. And then delta FTD is calculated to be 214.3 kilonewton, and we calculate the additional tension reinforcement, and it gives 493 square millimeter. The required tension steel for bending at support B is as required, which is equal to 1371 square millimeter. So the total as required near support B is 1371 plus the AS calculated from delta FTD. So the total steel area required for both bending and shear is 1864 square millimeter. So the provided steel is 6H20, so the S provided is 1885 square millimeter, so it's sufficient to resist both bending and also additional tension from shear. So crack control and minimum distance between bars calculation at support B is similar to span AB. So for that you can do the calculation on your own. So next we want to look at the design for span BC. So span BC, the design moment is 155.1 kilonewton meter near the middle of span BC. And then the ultimate shear force is just to the right of support B, which is 159.1 kilonewton. And then for span BC, we assume that we have only one layer of moment steel, so the effective depth is the same as span AB. So for the main reinforcement design, the K balance is 0.167 and the K calculated is 0.103, so it's less than K balance, so no compression reinforcement is required. And then we calculate moment arm Z, and it is 0.90 D, and as required as calculated is 882 square millimeter. After that, we calculate the minimum steel reinforcement. So this is similar to span AB design as well. So we get as minimum of 169 millimeter square and as maximum of 5000 millimeter square, and then we provide 3H20 to give as provided of 943 square millimeter. After that, we design the shear reinforcement with applied shear force of 159.1 kilonewton, and similar to span AB as well, we calculate VRD max at theta of 22 degree and VRD max at 45 degree, and the applied shear force VD is less than VRD max at 22 degree, so we use 22 degree in our design calculation. So for shear links with two legs, we calculate ASWOS to give 0.364, and then we use H6 links, which is 6 mm links with two vertical legs. So the area is two 6 mm bars, which is 56.6 square millimeter. So the spacing calculated is 155 mm. And maximum spacing based on 0.75D is 337 mm, and the spacing based on minimum link is 258 mm. So we use H6 at spacing of 150. Note that the H6 at spacing of 150 shear links are only needed near the supports where the shear forces are high. For the lower shear force portion of the beam, the minimum shear length of H6 at spacing of 250 is sufficient. The angle theta is less than 22 degree, but we conservatively take it as 22 degree. Therefore, the shear resistance of minimum length is 99.1 kilonewton. So based on the shear force diagram of span BC, we have 159.1 kilonewton just to the right of support B, and we have the shear force of 119.3 kilonewton shear force at support C. So based on that, we calculate the distance of the zero force location. So it's 3.7 meter from support B and it is 2.8 meter from support C. And then based on proportional triangle, we have this distance calculated to be 1.4 meter. So this is approximately the distance. We just take one decimal point. And then this distance here based on the proportional triangle here, we get 0.5 meter. So at this 0.5 meter region, we need H6 at spacing of 150, and from here onwards we have smaller shear force than 99.1 kilonewton, so we need only H6 at spacing of 250. And then for the region where it's 1.4 meter away from support B, we need the shear reinforcement of H6 at spacing of 150, because this region has larger shear force than 99.1 kilonewton. Next, we calculate the additional tensile force at support C. So at support C, the shear force is 119.3 kilonewton, and that gives delta FTD of 149.1 kilonewton. So the additional tension reinforcement is 343 square millimeter. The required tension steel for bending at support C is 25% of as required at mid-span, which is 0.25 times 882 to give 221 square millimeter. So the total required steel near support C is 221 plus 343 to give 564 square millimeter. So we can use only 2H20 to give as provided of 628 square mm near support C. For deflection, we calculate rho, which is as required over BD, so it's 882 over 250 by 449 to give 0.0079, rho naught is 0.0055, and rho prime is 0 because there is no compression reinforcement required. And then span BC is considered as an end span for continuous beam. So from table 7.4n, K is 1.3 for the end span of continuous beam. So rho is greater than rho naught, so we use equation 7.16.b to calculate the basic span to depth ratio. So that gives 21.7. And then the span of BC is only 6.5 meters, so it's less than 7 meters, so this coefficient is 1, or the multiplication factor is still 1, or we don't have to consider this at all. And then the multiplication factor for steel area provided is 1.07, is less than 1.5, so it's okay. Therefore, the allowable span to depth ratio is 23.2. The actual span to depth ratio is 6.5 meters over 449 mm, so it's 14.5, and this is less than the allowable LVD ratio of 23.2, so it's okay. For crack control, the limiting crack width is 0.3 mm based on table 7.1n with exposure class XC3. So the steel stress as calculated based on the quasi-permanent load is 220 Newton per square millimeter. So referring to table 7.3n, for steel stress of 240 Newton per square millimeter or less, the maximum bar spacing for crack control is 200 mm. So the bar spacing from our design is 3 bars here. So the bar spacing is 112 mm. So this is less than 200 mm. So it's okay. And then for the minimum distance between bars, the clear spacing is calculated using the spacing minus 2 times half diameter, so it's 92 mm. So 92 mm is larger than all the 3 requirements, so it's okay. So next we look at the detailing of this continuous beam. So for the detailing, we refer to the simplified rule of detailing for beams. So let's refer to this figure here, which gives us the dimensions and also the required steel for each of the parts of a continuous beam. So for the end span, 100% of the steel must be provided at the bottom near the mid span, and then near the end support you need 30% of the steel going into the support at a distance of 0.3L minus AL. So AL is taken as 1.125 effective depth D. And then near the inner support here also, 30% of what you have here should be extended into the inner support as well for the bottom bars. And then for the steel, for the negative moment at the support here, we need 100% of the steel over here up to 0.15L plus AL. And then we can cut off 40% and leave only 60% of the steel within the distance of 0.15L plus AL to 0.3L plus AL. After that, you can reduce to only 35%. But for a continuous beam with equal span, we can reduce it to 25%. So let us look at the span AB reinforcement, which we have positive bending moment near the midspan. So here, there are 2 lines here. It doesn't mean there is 2 layers of steel. You have to refer to the cross section to determine which are the 2 steel. So if you refer to cross section 1, the 2H20 here shows the 2 corner bars, and then this 2H20 here shows the inner 2 bars. So there are only actually one layer of steel, but in the detailing you can see 2 lines. Okay, so the layers in the detailing does not represent the actual layers in the steel layout, so be careful of that. And then we look at the curtailment here, where from the inner support here to here we can have a distance of 0.3 L plus AL. So 0.3 times 7000 plus 1.125 times 449 mm will give you approximately 1500. So this is approximated and rounded off. Next we look at the negative moment steel. So for the negative moment, the steel has to be on top of the beam. So here I have 3 lines, but the 3 line does not represent 3 layers. You have to refer to the cross section. So if you look at cross section 3 here, then the 2H20 here represent the 2 outer bars. And then another 2H20 here represents these 2 inner bars. And then this 2H20 here represents the second layer of the 2 bars. So from the simplified rule of detailing, from the edge of the support of 0.15 L plus AL, okay, it's approximately 1600 mm, we can reduce it to just only 60%. So here we have 4H20 as compared to 6H20. This is 66.7%. So 66.7% is more than 60%, so it's okay. We can cut off 2 bars starting from here. And then from 0.3 L plus AL, which is approximately 2600 mm, we can cut off the steel to only 35% of what we have here of 100%. But this beam is a continuous beam of equal span, so we only need 25% here. So 25% of 6H20 is approximately 1.5 bars. So we have 2 bars here, so it's okay. You cannot provide 1.5 bars. You have to have real numbers for your steel bar number. And then just now for span AB here, in fact in the simplified detailing rule you can reduce this to 30% of the bars here. Okay, but if reduce 30%, then it is less than the steel that you need for both bending and shear, as we have calculated for additional steel tension from shear added to the requirement for bending. We need at least 3 bars, but you cannot reduce 3 bars like that. It becomes not symmetrical, so we cannot cut off any bars there. And then on this side of the tension steel for the negative moment is similar to this side. After that we look at span BC. So span BC, near the middle of span BC we need 3H20. So we provide 2H20 plus another 1H20, and then somewhere near the support here we can reduce it to only 30%. So here we have 2H20, which is 66.7% of 3H20, so it's okay, it's more than 30%. As well as on this side also, in the simplified detailing rule, we can reduce this to 30%, but we have 2H20, which is 66.7% of the total bars here, so it's okay. And then the distance you just calculate accordingly. So this is 0.3 L minus AL. The same is for this distance as well. So By right, we should draw the shear reinforcement on the same diagram as well. But this diagram is not drawn to scale, so it becomes very messy if I draw the shear reinforcement together. So in actual detailing, when we draw this to scale on A1 size paper, then you can indicate all the bending and shear reinforcement in just one diagram. And then for the cross section, we look from left to right to see if there is any changes in steel arrangement. If there is change in steel arrangement, you have to provide a cross section. So cross section 1 here is shown in this diagram here, where you have 4H20 at the bottom and 2H20 on top. And then from here to here we have additional bars here. So you cut a cross section at the section 22 here, and section 22 has 4 bars on top and 4 bars at the bottom. And then the 2 layers indicated in the detailing does not mean that it's 2 layers in the cross section. Okay, we draw the line so that it's clearer to indicate where you need the number of bars. Okay, so these 2H20 are these 2 bars. So this 2H20 is these 2 bars here, which is the same layer as this 2H20 as well. And then when we move on to the right, we'll see that there is additional bars over here. Okay, so we cut across section 33. So section 33 will show 4 bars on the top layer and then 2 bars at the bottom layer for the top steel. And then for the bottom bars, we still have 4 bars. And then when we move on, there is a change in bars also within this region here. So we cut across section 44 to indicate 6 bars on top and then 2 bars at the bottom. And then we move on. So at section 55 we have additional bars here. So we have 1 additional bars in section 55 as compared to section 44. And then at section 66 there is a reduction of this bar which is already cut off. So left only 4 bars on top and then 3 bars at the bottom. And then at section 77 this bar has been cut off here. So the top has only 2 bars and then the bottom has 3 bars. And then at section 88 we have only 2 bars on top and this steel has been cut off. So we have only 2 bars at the bottom. Next we look at the shear reinforcement. So shear reinforcement for span AB will refer to this diagram here. So the shear reinforcement we need for H6 at spacing of 125 is within 1 meter here, and then the rest we can provide H6 at 250, and also at this right side of span AB of 1.6 meter we have to provide H6 at spacing of 125. So bear in mind that this is the center of the supports, okay, where the maximum shear is occurring. But when we provide shear reinforcement, we provide starting from the edge of the support. So we are starting the shear reinforcement here. So there is still some distance from the center of the support to the starting point of the shear reinforcement provided. So this H6 at spacing of 125, we know that we need to have it from here to here of 1 meter. Okay, but with the arrangement we provide until 1.5 meters from there. Okay, so this is more than 1 meter measured from the center of the support, so it's sufficient. Okay, and then on this side we need 1.6 meter away from the center of the support to the shear reinforcement provision of H6 at 125 mm. So we provide from here to here of 1625 mm. So it's already covering the region from the center to 1.6 meter to the
left.
of support B. So this is also okay. So and then the rest you just provide with H6 at spacing of 250. And then for span BC, we refer to this figure here. So on the left hand side of span BC, you need 1.4 meters of H6 at spacing of 150, and on the right hand side we need 0.5 meter of H6 at spacing of 150, and then the rest we can have H6 at spacing of 250. So remember that these are the centers of the supports. The shear reinforcement is starting from the edge of the support. So we need 1.4 meters here to have H6 at spacing of 150, but if we measure from the edge of the support, we need only approximately 1350. So we put H6 at spacing of 150 up to 1350 from the edge of the support, and then the rest we can put H6 at 250 spacing. And then we need 500 mm here measured from the center of the support to have H6 at spacing of 150, and then from the edge of the support is only approximately 450 here. Okay, so 450 is 3 times of 150, so we have 4 links there, okay, with spacing of 150, and then the rest of it is H6 at spacing of 250. So that's all for the solutions of this question 7 of tutorial 2. Thank you very much for listening.